Today, second day of MRI, magnetic resonance imaging. Today, generation of MR signals. RF coil acts as both transmitter and receiver in MRI. During RF pulse transmission, the coil cannot serve as a receiver. Hence, transmission has to be stopped periodically for enabling the RF coil to receive MR signals. A 90-degree RF pulse will flip magnetization to the transverse plane. Hence, immediately after a 90-degree RF pulse, the RF coil encounters only transfer magnetization MXY. The vertical component of magnetization MZ will be 0 at that time. MXY component is created by the phase of coherent precision of protons in the transverse plane. However, because of spin-to-spin interaction, they lose energy and phase coherence and presses back to their original relaxed state. When proton presses back to the relaxed state, the magnetization from transverse plane will spiral back to the external magnetic field direction. This type of circular movement of magnetization will induce a sinusoidal electric signal in the RF coil. This is figure. After a 90-degree RF, since the magnetization spirals back to the vertical direction, the spiral trajectory will induce a signal in the RF coil which has both sinusoidal and exponential decay component. This is received signal and receiver. So this is called free induction decay. The signal produced by the free return of M to the H direction is known as free induction decay. So what is free induction decay? It is a definition of free induction decay. And why it is called free induction decay, FID? Because when RF pulse is turned off, the spins begin to precess freely. The spins induce a current in the receiver coil. The signal start to decay with time. When a 90-degree RF pulse is applied to the longitudinal magnetization, it produces the following two effects. It flips longitudinal magnetization MZ through 90 degree to XY plane and temporarily destroy the magnetization in the longitudinal direction. This condition is known as saturation. This is called saturation. It also produces transverse magnetization MXY, a condition known as excitation, because transverse magnetization is an unstable excited state. So unstable excited state is XY plane. Relaxation process. What is the relaxation process in MRI? When RF pulse is switched off, two relaxation processes started simultaneously. Number one, first decay of transverse magnetization MXY and slow recovery of longitudinal magnetization MZ. Both these processes take place exponentially. Time required for both these processes depends upon the nature and physical state of the medium. The rate of decay and recovery characterized by the relaxation process conveys information about the structure in which magnetic moment is located. So this is relaxation process start simultaneously. First decay of mxy and slow recovery longitudinal. So when mxy will decay, then mz will recovery as per uh, transverse magnetization decay. As for time is required for this process, and also medium and physical state of the medium. Okay, relaxation process, this is mz mxy, loss of mxy, gain of mz, independent process. So loss mxy, loss when mxy is maximum, then mz equals to 0 when maximum is 0. Now gradually mxy decrease, then mz grows, mxy decreases, mz when maximum, then mxy 0, mxy 0. So this is curve T1 growth of magnetization in z direction, and T2 decay of magnetization in xy plane. So T1 is relaxation time. The term means the spins are relaxing back into equilibrium state. When RF pulses turned off, the spins will realign with external magnetic field lines by giving up all their excess energy. T1 is known longitudinal time because it refers to the time it takes for the spins to realign along the longitudinal z-axis. And T1 is also known as spin lattice relaxation time because spins relax back to their equilibrium state by giving up their excess energy to the surrounding tissue lattice. And if we consider that mathematical equation, recovery of mz at a time after the RF pulse is given by the relation mzt equals to m0 of 1 minus e to the power minus small letter t by t1. So m0 x, when mz max, then xy is 0. When this is when at a time when t small letter t equals to t1, then this will it will happen mz m0. So at t equals to t1, about 63% of magnetization will recovered. 63. And at t equal to t1, recovery will be 73.8. 100% recovery takes place beyond t equals to 5t1. And T2 relaxation time equal to the rate at which the mxy component decays. Hence it also transfers relaxation time. At TMT this. T2 decays occur 5 to 10 times more rapidly than T1 recovery. When T this is. So when RF pulse is switched off, mxy decay takes place because of the defacing of spin, which were in a phase coherent precision at the time of application of RF pulse. There are two phenomena that will make the spins to get out phase. They are interaction between spin and spin interaction and external magnetic field inhomogeneities. When two spins are close together, the magnetic field of one will affect the other. This is a major cause of defacing of spins. So major cause of the defacing spins is the close to each other. When the spins are spin interaction is inherent in the tissue and cannot be avoided. So since spin and spin interaction influence T2 relaxation time, it is also known spin relaxation time. When two spins are close together each other, and if one will affect the other, major about defacing time. Defacing effective T2. In order to account for the influence of magnetic field in inhomogeneity 1 T2, another decay times rate T2 star is introduced. T2 decay depends on both external magnetic field in homogeneity and spin-spin interaction, whereas T2 decay depends primarily on spin-spin interaction. Since spin-spin interaction cannot be controlled, T2 of a tissue which depends on this interaction is fixed. However, T2 star varies depends upon how uniform the main magnetic field is. T2 star decay is always faster than T2 decay. If magnetic field is homogeneous, T2 equals to T2 star. So T1 and T2 and tissue contrast. T2 characteristics of a tissue is depending upon how fast the proton is been defacing in that tissue. Rapid defacing result in short T2. And slow defacing results in longer T2. We take H2O, water. Proton occur wide apart in sparingly distributed water molecule. Hence, defacing because of spin-spin interaction is minimal in water. Because so T2 reaction time for water is therefore long, slow defacing. Solid molecular structure very complex solid. Therefore, protons are very close to another in solid. Hence, defacing takes place rapidly in solids. T2 relaxation time is for solids. Therefore, short. Fat proteins defacing is time for protein takes place a lesser rate compared to that solid, but a higher rate compared to the water. Hence, T2 has intermediate between that of solids and water for fat and proteins. So, transverse relaxation T2 for different tissue types at 1 Tesla. What will be there? This is CSF, gray matter, white matter, fat, etc. This is the carbon. And T1 characteristics. So this is T1 characteristics. The constant T1 is a tissue specific constant which tells how quickly the spins of a certain body tissue will emit their absorbed RF energy. The spins of certain body tissue will emit their absorbed. The T1 constant depends on size of the molecule and the type of its surrounding. H2O, small water molecule, can move quickly and randomly through its molecular movement. Hence, the energy released by a water molecule interacting with their neighboring molecules per unit time is very less. That is insufficient energy transfer. Hence, T1 relaxation time for water is long. Fat molecules are large and slow moving in their dense atomic lattice. Hence, the transfer energy is efficiently in short time. Hence, T1 of fat is very short. Solid sufficient, however, better than what. Hence, solid was into T1. This is the tissue fat H2O solid T1 T2. This curve. And